In this segment, we're going to talk about a technique which will allow us to calculate exactly the volume of a figure that is intricate like this one. Now, we're actually finding the volume of glass that composes this little candle holder. And it turns out that we can find the volume either with or without the candle included. Well, the technique involves the basic technique for a definite integral. And let's talk about that a little bit. Remember that when we talked about integration and definite integration particularly, we interpret that idea as the area under a curve. And we talk about the area between the graph of a function, the x-axis, and within a certain interval. And we talked about the concept of that as being one where we first take little bitty rectangles, and if we add the sum of the areas of a bunch of rectangles along here, then we approximate the area, and then we talk about the limit of a sum and so on. Well, we're going to apply that same idea to volume. Now, let's begin the discussion of volume like this. Now, I'm just taking a very simple type of figure and a predictable type of figure like a cylinder, and we know that to calculate the volume of this cylinder, the formula is pi times radius squared times height, so pi r squared h. Now, I want you to notice this, though, about the formula, that it is the area of the base times the height. Now, in order for us to apply our integration technique to this, what we're going to do is we're going to position our cylinder in a particular way along our coordinate plane. That is, we're going to take it and we're going to just twist it a little bit and position it like this. Now, notice that the x-axis is going right through the middle of it, and I might even position, just for convenience, the y-axis going through, right about here. Then I'm defining an interval from 0 to whatever point this might be, you see, to the spot where it comes out. Okay, so that's the idea. Now, the concept is that we're going to just think about the sum of a bunch of little volumes, and it's the volumes of little disks, hence the idea of disk method. But if we just kind of take a cross-section like this, and the thickness is kind of arbitrary at this point for this disk. So if I just make a cut through this rascal and think about that, and if I twisted it toward you and blew it up a little bit, it would kind of look like this. It would just be a circle, and it has some thickness to it, though, so we can think of it as a little bitty cylinder, you see. And so the volume is pi r squared times the width of this. See, we're thinking about little widths now, and it's the idea that we're applying the same concept that we did before, that we're going to find the volume of many such little disks, you see, and then we're going to narrow them, and the limit of the sum idea will give us the overall volume. All right, so that's the basic idea. Now, notice the notation here, big R squared for the radius of this. And when we talk about a little volume, a little delta volume here for the little disk, it's pi r squared times some delta x, some x interval, you see, over which we are slicing these little pieces of our cylinder. The overall volume is the limit of a sum, you see, of this expression, and it's just been rearranged to accommodate the situation. Now notice the delta, the thickness is approaching 0 here in this limit idea. This radius is associated with an x subscript I, if we're kind of counting the intervals you see along our cylinder and the delta x business. Well, all of that leads us to integration, and the volume then is the integral from a to b, the integral within an interval, you see, of the r of x squared, and that's this part, and then the delta x is the dx. The pi as a constant comes to the outside. And all we have to do then is apply the idea to a specific problem. Let's take a look at one. Suppose we have f of x as the square root of sine x, and this is the graph, and we're thinking about this. We want to find the volume of the solid which is formed by revolving the region bounded by the graph of this function and the x-axis, and it is revolved around the x-axis. You see, we just revolve that around. Now, and it's for this reason, this revolving idea, that this is sometimes called a solid of revolution, because we're actually just taking this graph and we're thinking about this region as almost like a flat surface, and think about revolving it around the x-axis. So it becomes a solid of revolution in that sense. And our interval, we're considering x to be between 0 and pi. All right, so that's the idea. Now, a couple of considerations are important in this. We have to define what our radius is. How does our radius change for the figure that we're talking about? Now, with our cylinder over here, it was kind of constant throughout our interval, but here it kind of changes, and it's just changing with the notion of the function. All right, so the actual function gives us the distances that we have here as the radius of our solid of revolution. And we have to define also the interval. Now right here it's kind of given to us in this problem. In other problems it might be a little more elusive. But we have to make sure we understand the interval and we understand the radius of the figure that we're talking about. Now, to emphasize the idea, the radius, which we have designated with our notation as r of x, is really just f of x. It's just our function, which is the square root of sine x. All right, and we use the form that we generated over here, and we just fill into that form. Notice the interval here, a to b, is 0 to pi, and the r of x is the square root of sine x, and away we go. We're squaring a square root, we get the radicand, and now we're just evaluating for our integral. And just pop in the values here. The cosine of pi, remember, cosine of pi is -1, so it's minus -1. And then minus, well, let's see, cosine of 0 is 1, so it's -1, so it's minus -1. And this gives us 2 pi then for the volume. Here's another one. Suppose we want to find the volume of the solid. Now this one has a little convolution in it, so let's read carefully. Find the volume of the solid formed by revolving the region bounded by f of x is 2 minus x squared and g of x equals 1 about the line y equals 1. Whoa. The region bounded by f of x is 2 minus x squared. That's this. And g of x equals 1. Well, here's the f function, here's the g function, g of x is 1, it's just a constant function, and the line y equals 1. Well, the line y equals 1 is just right here. So all we're doing is now the region bounded by this function and that function means that we're talking about this region, you see, and we're revolving around this line. And so it's a solid of revolution defined by this surface. There's a flat surface, we revolve it, it comes down like this. It kind of looks like the figure that we had before. And I'm going to try to draw it as symmetrically as I can, but I'm no artist. So we have a three-dimensional figure. It kind of looks like this. All right, now consider then that we need to talk about our bounds here. Where are we going from and to? You see, over what interval are we considering this? And we also have to consider the idea of our radius. You see, what radius we're talking about here. Now, the endpoints of the interval are at the intersections, at the intersection of this function and this function. It's the place where their y values are equal, if you will. And so all we have to do is set the functions equal to one another and resolve that situation. And I've done that here. Set f of x equal to g of x, and I've solved for x, so x is plus or minus 1. So the interval is from -1 to 1. All right, so here we have that -1 to 1. Now, what about the radius? Well, the radius of this rascal, it's kind of like it's from this line to the top of the curve. And to find that, it's like it's taking the y value associated with our upper function and then subtract the y value associated with the other graph. So it's really just f of x minus g of x, you see, to give us this difference all along the figure. So it is calculated this way. We take the difference in the functions, and so here's the f function minus the g function, and simplifying we get this. This is our radius now, so in our template here we just replace the information that we know. The interval is from -1 to 1. The radius is given by this expression, and away we go. Squaring here, we just expand, integrating, let's see, the integral of the 1, the integral here, the integral here, all of that is kind of self-explanatory, I think, with what we've had before. And now, let's see, we take the upper limit, we replace x with 1 everywhere we see it. We've got a 1 here, and then we've got a 1 here. 1 cubed is 1. So this is 2 times 1/3. Oh, that's minus 2/3. And a 1 here gives us minus 1/5. And then minus, let's see, -1 in place of x, and so on. So it's pretty arithmetic from here, and then we just collect as we normally would. We find the volume to be 16/15 pi for this figure. In the previous two examples, the solids were truly solid. That is, they didn't have any holes in it. Suppose, though, we drill a hole in the solid. We can still make the calculations we're talking about. Now, here's what I mean. Imagine that we have this cylinder, and let's say that we drill a hole through it from one circular surface to the other circular surface right through the middle. What kind of thing do we have when we slice it and look at a cross section? Well, we have a figure that looks like this. It looks like a washer. Now realize what this is. This is a cross section of that cylinder. So the cylinder would kind of come out this way and kind of go through the board, and we're just slicing it, and here's the cross section. Here's what the cross section looks like. Now, we're interested in the area of this cross section. And when we talked about the area of the cross section before, when it was truly a solid for that cylinder, it was just the area of a circle. You remember, it was the area of the circle times the height is what we started with, and then it was the area of this circular surface times a certain width, and so on as we developed the situation. But here, the area is the area of this washer. And we can really think of the calculation of the area as being the area of the big circle minus the area of the little circle. And let's see where that takes us. So the area of the surface of this washer is the area of the big circle minus the area of the little circle. Each of these is some pi r squared amount. The pi can be factored out, so we have big R squared minus little r squared. And the way that it manifests itself in the notation is like this. It's pi, then we have our interval, and we have this big radius associated with an x squared, and the little radius associated with an x squared. And we want the difference between those two because of that situation up there. All right, here's a problem that uses this kind of technique. And this situation occurs anytime you have a piece of the figure that's kind of dug out, you see. You're going to get this washer effect. And here it is. Here's the figure, but let's read the problem. It says, find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. Now, let's get a grip on this region, this region bounded by these two equations. Y equals the square root of x. Well, here's the graph. You see, just in the first quadrant we're talking about, and the graph of y equals x squared would be this. All right, and so we're just talking about this little region, but then you spin it around the x-axis, and you have a solid. You see, you have a solid generated in the same way that it was generated before. Okay, now we think about the notion of cross-section of this thing, and think about going across like this. You have this washer effect, because this little piece right here, this surface, goes all the way around, you see, and when you take a cross-section of it, it looks like that washer effect. Okay, so that's the idea. Now, we need to calculate here the outer radius and the inner radius in order to make the calculation within the integral notation. The outer radius we'll designate as big R of x, and that's the square root of x part. You see, that's that upper function that we had up here. And little r of x is the x squared. So in our notation now, and our notation looks like this, fitting our problem to the notation, we have, let's see, the interval is from 0 to 1, and we should calculate that. I didn't emphasize that very much, but the two graphs intersect here at an x of 1. All right, that's kind of an important feature. And then the big R of x is, the big R is the square root of x, it's squared, and little r is x squared. And so let's see, squaring the square root, we get the Radican. X squared squared is x to the fourth. Let's see, we integrate these two separately. The integral of the x is x squared over 2, and for this it's x to the fifth over 5. And so we run up here, and notice that we're in the interval from 0 to 1. So let's see, for the 1, we replace these numerators with 1s, and we have this, minus, and the 0 replacing these numerators, that just goes out. And then we find common denominators here and evaluate to find the volume to be 3/10 pi or 3 pi over 10. This next one involves two nuances. We have the situation that we had in the previous problem, plus we have an additional nuance. Let's read the problem. It says, find the volume of a solid formed by revolving the region bounded by, and we have several equations here, about the y-axis. So we're going to revolve around the y-axis rather than the x-axis in this one. So that presents us with one of the nuances. Now let's talk about these bounds. We have the graph of y equals x squared plus 1, and that's this. You see, that's just this little curvy part. And then y equals 0, and that's the x-axis. X equals 0, that's the y-axis. And x equals 1. X equals 1. Okay, that's this line. So we're really talking about this little region right here, and we're going to revolve that around the y-axis. So we just swing it around here, and look at what happens. We have this dish effect occurring up here at the top, and we have a true solid, which is a cylinder, right in this region. And we can actually think of the situation in two parts if we want to, and we're going to do that. And that's the other nuance here. We have two parts, and we're also having to integrate with respect to y. You see, because after all, we're thinking about our radius. Instead of thinking in terms of the radius of our cross-section of the figure being kind of up and down, we're having to change our thinking and think about it this way. So we think about little sort of rectangles in the cylindrical part. We're thinking about those rectangles that go in this direction, you see. And it's pretty easy to think about this radius, isn't it, for the cylinder part of it. It's just 1. It goes from 0 to 1, so that radius is just 1. That's pretty easy. But what about the part up here? Well, we have to make the calculation for a little rectangle that might be, for example, right in this neighborhood. You see, now how do we do that? Well, we're looking for horizontal distances here, so rather than have a function which is y in terms of x, we need to rewrite that as x in terms of y. So I'm thinking about this curve, which is y equals x squared plus 1, and I'm thinking about solving it for x. I want to write x sort of as a function of y. You see, just kind of the other way around. So it's solving this, we find that x is the square root of y minus 1. So the radius in terms of y is the square root of y minus 1. So that's what we're talking about when we have that distance right here. You see, it is a x distance, a radius in terms of y, you see, is that distance, and then 1 is this overall distance. So it's the difference in those two that will give us this little radius unit that we're after. All right, let's set the problem up like this. We're going to find the volume in pieces. We're going to say, well, we have a cylinder part, and we might say we have a dish part. The dish part has this washer effect going on for those cross sections. So we would have, well, let's see, for the cylinder part, it's pretty easy. We have now notice the notation that I'm using here, and we haven't talked about this before, but I'm talking about an integral along an interval along the y-axis as c to d rather than the confusion of a to b. We used a to b before on the x-axis, so we'll use c to d here. And it's a radius in terms of y squared, dy, and then over here it's a difference in radius units. You see, a difference in radius value squared to give us that washer effect. All right, so let's fill in the information that we know. Now the interval here, and we probably ought to pay a little attention to our values here. This is 1 and this is 2, it turns out, on our coordinate plane. And the intersection of this x equals 1 and this curve turns out to be at 1, 2. All right, so that's kind of important. So our overall interval here is from 0 to 2, but we're taking it in parts. The cylinder part is from 0 to 1, and the dish part is from 1 to 2. So that's why here we're integrating from 0 to 1, and the radius along that entire interval is just 1, and it's squared. And then over here, we're integrating along the interval 1 to 2, you see, along the y-axis. And again, the big radius you see all the way out to the edge of our figure is 1, and then the curvy part is the square root of the y minus 1. And now it's pretty much arithmetic. We just clean it up quite a bit. The 1 squared is 1 here, and 1 squared is 1. Squaring, we get the radicand, but we have the minus sign, so we have minus y and then the plus 1. The 1 and 1 gives us the 2, so we have the 2 minus y dy. And now we integrate as we normally would. This is 1, and the interval is from 0 to 1. And this is, let's see, 2y, then minus y squared over 2, and then from 1 to 2. And then back over here, let's see, the top end is just 1, so it's 1 pi, and 0 in place of y goes out. So it's just pi for this business. And then over here, let's see, we have a couple of parts. Replacing the y with 2 in both spots gives us this, and replacing with 1 in both spots gives us this business. And when the smoke clears on all of this and we collect it out, and it's pretty easy to see, this is 2 squared, 4 over 2 is 2. And this is 4. So we have 4 minus 2 is 2. And then minus this 2, all of this stuff goes out. So minus minus is plus, and this is just 1/2. So this is 1/2 pi plus pi, 1.5 pi, or 3/2 pi, or 3 pi over 2 for the volume of this overall figure.